Why hello there, I am Shane's Potato, and welcome to my YouTube channel. Now you may be wondering, what happened to my super awesome absolute peak intro? And I have an answer for that. Now unfortunately YouTube is stupid and they copyrighted me for the music I use in my intro and probably my outro as well, so I'm not going to be using those in this video, but I hopefully should have something figured out by the time I post my next video. But ignoring all of that, that then brings me to what the actual topic is of this video, and that's what I'm going to get into. This is my theorem. You probably remember it from the last video, which I just kind of had as a background prop there where I ran over a little bit briefly, except this time the entire video is going to be about this. Now unfortunately this video is going to be relatively straightforward and very purely mathematically based. Probably a little boring, probably a little underwhelming, but I need to do it nonetheless, so I want to get my point out there. So without further ado, let's get into it. Alright, we're going to start off by going over the base equations. We have this one, which I explained in the last video, is for finding the velocity of an electron. This one, the value of a single coulomb. This one, the value of Coulomb's constant. This one, again, the value of finding Coulomb's constant, except this time is expressed in 1 over 4 pi epsilon null. Epsilon null here, its value, which is vacuum permittivity, as I said, which is essentially a vacuum's ability to sort of hold an electric field and how good it is at doing that. This equation is for finding the force between two electrons, which is equal to Coulomb's constant times charge 1 times charge 2 divided by the distance between the two charges. This, we have Newton's classic equation, force equals mass times acceleration. This equation is a little different. It's for finding the force between two ions, equal to distance between those ions times the square root of the mass of the ion divided by 2 electron volts. This one, these two are the same values, the distance between an ion, like I said, which is equal to the cubic root of 1 divided by the density of ions. This represents the charge of a single electron, 1.6 times 10 to the negative 19th. This represents the mass of an electron, which is 9.9 times 10 to the negative 31st kilograms, still in kilograms for whatever reason. And finally, this one is the inverse square law. These equations are really just little reference equations that could just be linked to the theory through whatever means possible. That's why I had them up here. Next up is my proof. This is my actual sequence of equations to try and prove whether my final equation here is right or not. These equations sort of lead up to the final equation, which I obtained through just simple trial and error. I actually forgot to talk about it in the video, but just for reference, the first line of the proof is just a set of given equations, just to actually establish everything going on. Now, this equation shows that the velocity of a molecule is equal to the velocity of the electron divided by the mass of that molecule squared, in an ion thruster, of course. Now, I did make a little error writing it down here where I accidentally squared the velocity of electron and then divided the mass, but in reality, the whole thing itself should actually be squared. Now, moving on, this just serves as a little placeholder to represent that the molecule itself is the friction over the electron when it's moving. So when that electron exits the anode, moving close to the speed of light or somewhere around there, when it ionizes that atom in that molecule, it's going to significantly slow down, and that's why it's just saying that that's the friction over it. Pretty straightforward. This equation here is also significant. It says the velocity of that molecule entering the ion thruster is going to be equal to less friction, which will equal greater velocity exiting it. Pretty straightforward there. This is sort of another revised version of this equation. It now factors in the initial velocity. So the velocity of that mass exiting the ion thruster is equal to its initial velocity plus the velocity of the electron divided by the mass squared in total. Now, moving on, we have these little base extra equations. These are sort of just going to be added on later as we build our final equation. This just shows to factor in the amount of electrons per second, the distance between the anode and the cathode in millimeters squared, and this little placeholder. This equation itself actually serves no mathematical significance, but it serves as a reference point. It says that any value of n is an element of the molecule, or the type of molecule. N, we're just representing what type of element is it. Is it oxygen? Is it hydrogen? Is it nitrogen? Is it xenon? What is it? Just serving as a placeholder to represent and just as a reference to remind you that you need to factor in what type of element it is, because that's important. How heavy is the atom is going to change how fast that electron can accelerate it, just because more mass equals more friction. All right. Now we have the next line. Now this line is just sort of building on trying to assemble the final equation. So we start off here, we have the velocity of a molecule, again, or the mass, is equal to any value of n as an element of m, now we're factoring that in, times the initial velocity of the molecule plus the amount of electrons per second, times the velocity of the electron divided by the distance between the anode and the cathode in millimeters squared, all divided by the total mass of the molecule, and squared, of course. Then moving on, we have to factor in what unit we're actually using. And the unit we're actually using is millidaltons. Now, the fact that we have to use millidaltons is something that has actually made me suspicious that this may all be wrong. Now, of course, there is a potential that the actual math itself is wrong, the theory is right, but the math is very significant in proving whether the theory itself is correct. Now, millidaltons are just a very, very, very small unit to sort of account for every tiny little bit of mass. It's almost like accounting for the number of molecules or atoms that are actually present and how much they weigh in those little units. Next, we have this equation, which is sort of factoring in a derivative, saying that the velocity of an electron is equal to the velocity of the electron, but then derived by the velocity of that mass, or the molecule, which could be equal to the speed of light, but it can't exceed the speed of light due to the laws of physics, and it can't go lower than 0, again, due to the laws of physics. Just sort of factoring that in as a little placeholder. Now, moving on, we have this new complete equation, except this isn't a complete equation, it's just a more greater example of speed equation. Now we have the velocity of the molecule is equal to any value of n as an element of the mass. Now we factor in a derivative with, like we said, top limit speed of light, lower limit is 0, times the velocity of the initial mass, plus this time we're using an absolute value, just sort of to prevent negative voltages and negative amperages from screwing everything up, because obviously you can't get a negative value out of this equation. So same thing, the amount of electrons per second times the velocity of the electron divided by the distance between the anode and the cathode squared, all divided by, except this time, mass in millidaltons of the molecule. Now here we reach the last part of the proof before we get to the actual final equation itself. This sort of just stating it that alpha times n, or what type of element is it, is an element of mass in millidaltons. Alpha just sort of representing the total number. It's just a variable. How much mass is there? Then divided by seconds. Now, it's sort of divided by seconds in how long is the ion thruster running. How much mass is passing across the ion thruster, across the anode and the cathode per second. That's why the divided by seconds is in there. With that, we then lead to the final equation. Now, the final equation here states that the final velocity of that mass exiting the ion thruster is equal to our little placeholder, any value of n is an element of the mass, then our derivative, top limit c, lower limit 0, times the initial velocity of that mass plus the absolute value of 1 coulomb times the amount of amperage to find the total number of electrons, times, finding the velocity of the electron or how much energy it has, the square root of 2 times the charge of the electron times the amount of voltage divided by the mass of that electron, absolute value bar, divided by the distance between the anode and the cathode squared. All of that divided by the total mass of everything passing through in millidaltons per second. And all that is squared, and then this at the end just represent that it is derived by a velocity of the mass. Not specifically initially or after, just total velocity of the mass. Now, this is a pretty big, scary equation with all the funny numbers in it or whatever, but overall, I think it's a fairly solid starting point to actually proving whether this theory is correct or not. Now, of course, I don't know the answer to that. I think it's correct personally, but I don't know. If some physicist was watching this video, they could entirely agree with me or call me out that I'm a complete idiot. I have no idea. But with that, that's pretty much everything about the actual theorem itself. So let's move on to the next part. Now, there's a pretty big question here that I haven't really answered, and that question is, what would an actual rocket like this look like that factors in my equation? And that's a great question. Now, what I would be looking at is essentially a combustion rocket, ion rocket hybrid, where essentially you strap an ion thruster onto the end of a very large combustion rocket, and you have the exhaust, the combustion rocket for the ion thruster. And hopefully with that very intense initial mass and a couple of stages in the ion thruster, you could get the exhaust moving close to the speed of light, at least if the theory is correct. But of course, a rocket like that would have a lot of technicalities to it, including a very complex cooling system through the ion thruster so everything can handle that intense heat from the combustion rocket, and a lot of power draw needs to be used in such a large ion thruster to keep it running, especially in that environment. Now, one of the biggest problems is having actual humans moving at that speed itself, or more likely accelerating to that speed. One common misconception is that if a person moved at the speed of light, they would vaporize, which is incorrect. Matter of fact, if they accelerate instantaneously to the speed of light, then they would vaporize. But if you're moving at a constant continuous speed, you won't feel anything. So the solution may seem simple, just accelerate slowly to the speed of light. But then another problem comes in, the time it would take. Now, on Earth, we experience about 1 g of force, and if you were to accelerate about 1 g in a ship to the speed of light, the problem with that is that it would take about 2 years to reach that speed, and if you factor in deceleration back down to normal speed, that's another 2 years. So, yeah, if you want to factor it in that way, it could significantly cut back the amount of time it takes you to get somewhere, but the amount of time it takes to accelerate is just way too long. Now, another problem also being particulates in space. Now, space is mostly empty, but it's not completely empty. If you're moving at the speed of light and a little speck of dust hits your ship, it could probably vaporize it just because of the intense velocity and energy that that ship has if it's moving that fast, which means you would need some kind of force field technology in order to prevent that from happening. Of course, it is possible to potentially build a force field technology to avoid hitting very small objects, but larger objects, you just die if you hit it, which would kind of be fine because you're more likely to hit a small object than you are to hit a large object. Is there a lot of risk at play? Yes, but that comes with everything. Now, from this, it may seem like moving at the speed of light is damn near impossible, which, no, I think it is possible, and I think these little drawbacks and obstacles can be overcome through more technological advancement. After all, we are in the most technologically advanced age of the entirety of humanity, and we're only accelerating forward. So I think that we could potentially get to a point where those technologies, in order to avoid those problems being in place, moving it close to the speed of light or accelerating to it, could be potentially overcome. But with all that said, I think that's pretty much everything. Again, I have no idea if my theory is correct. I strongly believe it is, but I can't know without proper testing. So, am I right? Great question. That's all.